It's the same. What's the name? That was 10 minutes.
I want to just finish up on second derivative test. I didn't quite get to that last example, so we'll do that. And today we're really just putting things together. Curve sketching is just gathering information from the function, whether it's x-intercept, y-intercept, vertical asymptote poles, and gathering information from the first derivative function, the first derivative test about where is the graph going to exhibit positive slope, negative slope, relative max, relative min. And then the test for concavity will help us decide, okay, which regions is the graph going to have concave up, concave down, point of inflection. And then with all that data, we can get a pretty good sketch of the graph. Okay. Properties from the function, properties about the information about the slope, and then information about the concavity. Okay. So we're really just putting it all together. And I forgot to put this in your calendar, but your AP practice from 5.3, I'm going to split it into 3 parts here. So yesterday you guys did 1 through 4. Tonight go to 5 through 10, and then Monday I'll check 11 through 15. Okay. Tomorrow, what we're going to do is we're going to see if we can sketch a derivative graph. So AP exams, they love to do this. They love to give you a derivative graph and ask you information about the original graph. So we'll have to explore that in terms of if you're looking at a derivative graph, can you tell me information about how the original graph is behaving? Okay. Okay. Also, I have your test for you. So let me give that back to you at the end of class. Okay, I'll give that back to you in class. Okay, so let's see. Yeah, just remind me around 10 o'clock that you want that I'm supposed to give your test back. Okay. Let's go to your okay, page 23. We didn't quite get to do that full example. So let me do an example of oops, not 23. Yeah, second derivative test. Yeah, so page 23, example 2. Okay, it says find the relative extrema using the second derivative test. So we're not going to go through the slope sine line, okay? But we're still going to do the same steps initially as first derivative test. We're still going to find f prime. We're still going to set f prime equal to 0. We're still going to find critical points, but then from there, we're going to go down a different path rather than putting it onto our sine line. Okay, so we want to find relative max, relative min. Let's find the candidates for relative max, relative min. They're going to come from f prime. So let's find f prime. Derivative is we set equal to 0 because this is where we want to find our candidates for max and min, relative max, relative min. This is factorable here. Double check this here. 3x squared minus 9x plus 1x, that's minus 8x minus 3. Okay, I can solve for x here. X is -1/3 and x equals 3. So we have 2 candidates for relative max, relative min. Normally we would, if you had a choice, you probably want to go through first derivative test and just put it onto a sine line and then test your interval. But we're going to go down a different path. Okay, but we know these are our candidates, right? At least we know that these are candidates for relative extrema. Sorry. Okay, so we're going down a different path here. We're going to use F double prime to help us gather conclusions about whether these are relative max, relative min, or one more thing I forgot to mention is that if your double prime gives you 0, that means the test is inconclusive. That means your second derivative function is not going to give you enough information for you to claim whether or definitively say that your point is at a relative max, relative min. Okay. So let's find second derivative first. What's the second derivative function? 6x minus 8. Okay, are we going to set this equal to 0?
No.
No, that's different, right? That's test per concavity, right? We're doing the second derivative test, which is testing the candidates for relative extrema into F double prime. Okay, so I want to just make sure that, you know, everything kind of can kind of be confusing because all the steps are kind of the same, but they're different, right? We want to kind of have an idea what the purpose of this process is. Okay, so we're going to insert -1/3 in for x because we want to see if is the graph concave up or concave down at these points, and that's going to help us conclude what extrema is occurring there. So f, let's test -1/3 first. So 6 times -1/3 minus 8. Right? What's that equal to? Get to say it again. -10. Okay, so I just want us to look at that number and just be aware that this number is not that important, right? Sometimes students see this and they feel like, wait, what to do with that -10? Does that mean it's a point? Does it mean it's slope? This is concavity. We don't have to worry about what does that -10 mean in terms of what the graph. We just have to worry about the fact that it's what? That it's negative. Yeah, that's really the whole takeaway that you need from this to help you make your appropriate conclusion. Now, I get a negative concavity or negative second derivative value. What does that mean? That means at this point, this graph is concave down. It helps if you can draw a picture of it and convince yourself the only place where I'm going to get a slope 0 and it be part of a concave down graph is if the point is a what? Relative max. So there it is. So relative max is at x equals -1/3. Now, can I say that my order pair is -1/3, -10? No, this -10 is not the order pair, right? This is just some number that is telling you that it's concave down. If I want to find the full order pair, I will have to go back to the what? Original function. Okay, so I just want to keep reminding us what the roles of f prime, and f double prime is doing so that we don't get thrown off by it. Okay, but in this case, I think we only need to provide x value, so this is good enough. But just be aware how easy it is for students to look at this and think that this is a relative minimum because you see that negative, but we really want to equate this with concave down. So if you can verbalize concave down and draw the picture, then I think you can avoid the mistake of thinking that this is a relative min. Okay, so now let's look at the other candidate, which is 3. Let's insert 3 into the second derivative function. This time, what do I get? This time I get 10. But the number is not that important. It's the fact that it's positive. Okay, so positive second derivative value means my graph is concave up. You don't have to draw your picture, but I think it really helps. Concave up. I know that at 3, there's a slope 0. So if there's a slope 0 and it's part of a concave up graph, this point must be a relative minimum. At x equals 3. So yeah, another place that I see students have trouble is just knowing what to do with these numbers, and they feel like they have to involve those numbers. in their answer, but it's just really the sign that we're after, okay? Whether it's 24 or 68, it doesn't matter. It's whether it's positive or negative, and that's the takeaway that you want to get. Okay, so I was also trying to think of, why would someone want to do second derivative test when first derivative test is right there? This may not apply to us in terms of the problems that we're going to see, but there are times when it's faster to find the second derivative and plug in than trying to plug a value into a messy derivative function. I know it's not going to quite apply for us here, but there are some instances when it's just faster to find the second derivative and plug in the value and determine whether it's a relative max, relative min. But 90% more, 95% of the time, we're just prefer to go to the first derivative test, which is fine. We just have to have knowledge of second derivative test and know how to apply it when an AP exam problem forces you into using it.
Okay. I can use it whenever I want to, unless if it doesn't equal 0.
Right, that's right. You can always use second derivative test unless it equals 0. Then you're kind of stuck having to go back to the first derivative test. For the most part, yeah, I can't think of an instance when it's equal to 0 that is relative max, relative min, but apparently there are examples where it's inconclusive and it's possible where it could be neither relative max or relative min. Right. But just know that it's not foolproof and it's not the preferred method that we want to use. We prefer first derivative test, which is fine. Okay, so just wanted to make sure I go over that. Let's go to our curve sketching page here. Okay, so we'll start off with a polynomial. Polynomial is a little bit easier. There's less issues with it in terms of things we can pull from a graph, but okay, so first off, we know this is a polynomial, right? So there's not going to be any breaks in the graph. There's no holes. There's no vertical asymptotes. So at the bottom here, these are the information we're going to eventually try to gather. So we don't have to worry about vertical asymptotes. Don't have to worry about horizontal asymptotes. We can find x and y intercepts. Okay, so let me put some notes here. So the way we find x-intercept. Okay, so we set the numerator equal to 0, and then we solve for x. I know there's no denominator here, so there's nothing to worry about in terms of basically you're setting the equation equal to 0. And then to find y-intercept, you're replacing all of your x's with 0, and then you're solving for y. And x and y-intercepts are just nice to help give us some anchor points for us to put onto our graph. Not really pretty points, but we have some x-intercept there. Y-intercept. Plug in 0 for X and it's really just 0, 0. Yeah. So if you, whenever 0, 0 shows up for one, it's going to be for the other as well, since it acts as both the X and the Y intercept. Okay. So now we're going to find information from the slope perspective. So we're going to find F prime, go through first derivative test, create your sign line, discover whether graph is increasing, decreasing, relative max, relative min. And then after we get all that information, we're going to go to the second derivative function and then do the test for concavity. Okay. All right, so try those steps and I'll show the work and see how it will do. I'll be right back. Okay, so F prime, let's go through power rule. We can factor out the negative 15x squared. And we're to see that continue factoring with x squared minus 1. We have 3 critical points, so -1, 0, and 1. Some of these numbers are a little messy, so I will let you use a calculator on this next assessment. Okay, so I'm gonna, I tested -2, I tested -1/2, I tested 1/2, I tested 2, all back into the first derivative function. I'm just trying to gather the sign. A positive would mean that my graph is rising, a negative would mean my graph is falling. I like to use those arrows to kind of help me see the flow of my graph, because once I see these arrows, it's easy for me to see there must be a 1 and -1 here, based off the path there, right? When you see relative min. At 0, you see that the graph is kind of rising, but it's leveling off, but it continues to rise again. So there's neither a relative max, relative min at 0, but then at 1, with the graph rising and falling, you can visualize there being a relative maximum at x equals 1. And if I were to ask you for the full ordered pair, of relative min and relative max, you would insert -1 and 1 back where? Original, yeah. The original is always where you look for physical location, once you've established what you know is happening there. So I kind of have an idea of the general flow of my graph. So now I'm going to move on to the second derivative. So go back to my form without the parentheses. I can just do power rule twice.
Why'd you make it equal to -30x times?
I just took out the GCF.
Oh.
You could also just take out 30x as well. I just decided that I wanted the x squared to be positive, so I back out the negative as well. Okay, so -30x gets factored out. Solve for x, I have 3 critical points. 0, plus or minus 1/2, which is really √2/2. √2/2 is around like 0.7, so you can test 0.5 and -0.5 on either side. You can test -2 and 2 on the other sides there.
Second derivative is just -16x³ plus 30x. I mean. This is the first derivative is -15x⁴ plus 15x². So like I don't know. I don't know when you add it to the right of the equal sign.
Oh, you talking about the factoring process?
Yeah.
Okay, so if I factor out a -30x. If I factor out a -30x, that means I'm dividing everything by -30x.
Right.
So that leaves me with 2x², and then this is still a -1. No. And then from here, I'm just setting this equal to 0 and finding my critical points.
Yeah, well, but forward it's set equal to this. The original, it's set equal to -60x³ plus 30x. That's what's confusing.
Oh, these are the same, right? I just decided to clean up from here. This is still f double prime.
Okay.
Yeah. All right, everybody okay with the process, critical points, testing each interval, and then interpreting the sign that you get back in return. So a positive would mean that the graph is going to exhibit concave up. Negative would mean it exhibits concave down.
But there's a square on the other side. So.
Okay, don't worry about the sketch of the graph yet. I do want to talk about how I want you to go about doing it. But right now, I'm just seeing if we can gather enough information, right? We know there's relative min, we know there's relative max. How many points of inflections do you see? 3, because there's a change in signs, right? There's got to be a change in signs accompanied with a critical point in order for there to be a point of inflection. Okay, so now at the bottom of the page, we're just going to gather all that information and put it you guys don't have to write out all these because statements for now. I just want you to know that if I were to ask you to justify, this is what your justification would look like. Okay. Because relative min is because f prime changes from negative to positive. Relative max is because f prime changes from positive to negative. Increasing because f prime is greater than 0. Decreasing is because f prime is less than 0. Concave up is because f prime is greater than 0. Concave down is because f prime is less than 0. And POI is because f prime changes signs. But really, we're just pulling all that information from our sign lines. Yes.
There'd be like one of the inflections on the first derivative of the function.
No, the first derivative function is not going to tell you concavity or point of inflection. It's going to just tell you what the slopes are. So it'll give you relative max, it'll give you relative min, or neither. Right. But anything that is curvature wise, that's going to come from your second derivative sign line. Now, critical points may show up on both your sign lines, but they'll be showing up on both sign lines for different reasons. Maybe it's a slope 0 and a potential point of inflection, then it would show up on both sign lines, but for different reasons. Okay, any questions about how we're able to, because everything here we can just pull from the sign line. Now, some of these values though are y values that come from the original function. I also wanted to kind of talk about how I want you to think about the graphing portion, because it does feel like a lot to put, wait, I got to put all the slopes and curvature onto my graph. You know, how am I going to organize all that onto my graph? But I want to make sure that you guys are good with pulling this information from your sign lines and those numbers. Yeah.
For the interval increasing, can you just write like -1 to 1?
Yes, you can. I like to separate it because you won't get points off for separating. Sometimes though, I do see some students merging things together and then they forget there's a vertical asymptote there. And then so if you merge together, that'll be incorrect. So I like to just always separate. That way, I'm never going to get points taken off. I don't have to worry about, wait, should I merge or should I not merge? But if you merge and there's just a slope 0, then that'll be fine. You won't get points taken off, but you'll get points taken off if this was a vertical asymptote. So I just like to separate. That way I don't have to worry about, wait, do I merge or do I separate? Yes, you can separate this. I'm sorry, you can combine that. Okay, are we good with the pulling the data standpoint? Okay. Let's talk about the graph. Okay. So I like to just gather the most important points, and then we're essentially going to be connecting the points together. But we know that there is a x-intercept at 0, 0. We know there's an x-intercept at what is it, plus or minus 1/2. So sorry, plus or minus √5/3. 5/3 is close to 2. Square root of 2 is like 1 point something. So I know it's going to be somewhere here. I'm just going to just ballpark the value there. I know that I have relative min and relative max. My relative min and max are coming from -1 and 1. And if I plugged into the original function, I get -1, -2, and 1, 2. And then points of inflection. I know points of inflection is going to land somewhere between my intervals here. So -√2/2, that's like around like -0.7, -1.24. You don't have to be too exact. We should have some target points to go after here. So √2/2, that's around 0.7, 1.24, somewhere here. So really, we're just connecting these points together, right? Okay, so let me go back to the sine line. And I want us to do two versions of this graph. That way it doesn't feel so overwhelming. Trying to figure out, wait, I got to do the slope and the curvature all at the same go. So I know there's a relative minimum at -1. I'm just going to follow the path of the graph. I'll just do it very lightly because this is not my full graph with all the curvature. But I do know the path of the graph is going to do this, right? It's going to be a relative minimum at -1. It's going to rise until it hits 0. And once it hits 0, it's going to flatten out for a moment, but it's going to continue rising until it hits a relative max. And then it's going to fall down. It's going to keep going down relative to. Okay, so I don't have the curvature figured out, but at least I know how the graph is going to flow. Right? I'm just basing this off my slope sine line. Right. Now, let's focus on the curvature portion, because I know that I have points of inflections at 0, second surge of sine line here, -2/2, 0, and √2/2. So I'm going to highlight those points. And now I'm going to give the proper curvature along the path of the graph. Okay. So I know that between -infinity to -√2/2, my graph is concave up, so it's going to have a U shape to it. So I'm going to just try my best to create that U shape up until my first point of inflection. And then it's going to switch to what? Concave down, but it's not going to show the full concave down shape. It's just going to be that curvature up between these 2 points. Right, so it's going to take on this shape, right? It's not going to do the full concave down, but it will have that curvature until it reaches the next point of inflection. And then it switches over to back to what? Concave up, but just the curvature of it, not the full concave up. Between these 2 points, I want to kind of have that U-shaped portion. And then after that, it's all what? It's all concave down. And that way it just feels less intimidating trying to do too many things at once, right? Just use a dotted line to connect your dots first, and then you can go back and revise the curvature between each of the points. And that way it just feels easier, I feel. Yeah. Separate.
Like separate
Yeah.
them. At that one point, would there not be a point where the derivative equals 0?
Yes. So, you're saying how we're able to combine it if there's a slope 0. So they say that you can make an argument that this slope 0 is part of increasing, because right before it's increasing, right to the right of it is increasing, so we consider it as increasing. So there's an argument to be made where you can put it all under part of increasing, even though there's a slope 0. So, but I like to separate, but you won't lose points as long as there's no pole or asymptote here, if you want to merge together. Okay, let's just do a little bit of page 35. Now, what do you notice about this function that's different than the previous one? Yeah, there's denominator, right? And there's denominator. We know there's going to be, well, denominator variable. We know there's going to be some breaks along the graph. So we can find the fact that the denominator has 9 minus x squared. We know there's a vertical asymptote. We know there are no holes because there are no common factors between numerator and denominator. And also, we're going to be experiencing horizontal asymptotes because horizontal asymptotes is wherever limit approaching infinity is going to give us, right? And with limit approaching infinity, we know that we compare degrees. Yeah. So we know there's a horizontal asymptote at y equals -2. So the nice thing about asymptotes is that it kind of gives you some framework about your graph. It kind of gives you some boundaries. You know your graph is going to kind of be living around and around those asymptotes. So we have two vertical asymptotes, 3 and -3. Horizontal asymptote is at y equals -2. Do we have x-intercept here?
Yes.
Okay, that the numerator equal to 0, 2x squared equal to 0, x is 0. Do we have y-intercept here? Yeah. 0/9, right? Replace x with 0, still 0/0, right? Oh, sorry, 0, 0. So,
What if the degree on the top was lower, then it would just be 0.
it would be 0, right? So if it was 2x cubed over 9x minus x squared, sorry, 2x, 2x over 9 minus x squared, their horizontal slope would be at y equals 0 because the denominator is higher.
And if it was greater, there's no horizontal.
Yeah, if the top has a higher exponent, then there is no horizontal asymptote.
Okay.
Exactly. There will be slant asymptote, but we don't worry about it in this course, potentially. Sorry. If the degree is 1 higher than the denominator, there will be a slant asymptote, but we don't have to worry about slant asymptotes for the curve sketching that we do.
Please check your schedule in Infinite Campus and identify your homeroom class. It will be located at the bottom of your schedule and report to your homeroom class during advisement period today. Make sure that you bring your FCS student device. If you receive a pink pass for testing, report to the location on the pink pass for the advisement period. All 12th graders should report to the auditorium. Thank you.
What do we do?
Okay, we'll finish this tomorrow, but what rule do we have to go through to find the derivative? Yeah, so we'll walk through that process tomorrow. Let me pass your test then.
That's why I think you can do that. I didn't see it. Can I give you back to Mr. Let me have some competition for you.
You're so welcome. There's that. You have to. Okay, every other day. So you got to slow down. Every other day. Would you just? I did.
Even if it's like a question, you still like.
Runs this. I didn't break my life.
I just didn't plug it.
That's mine.
Oh, okay, yeah, you didn't plug it. That's thank you, man. I just got one since read it.
But he's still.
Yeah, I got this wrong. I just, I know that I can see it. I should be fixing it. It doesn't make the Okay, what is they we don't have points off to get on the one. Those are the 3 points. But like, you know, a lot of injury time. Oh, it's like wrong class. So we just
Right, I see where I messed up.
We talked about it. For this one, for this, I did it wrong because I was overthinking
So Jack,
built in. But I initially was
Right here.
correct here.
Yeah.
And you said
Right
it's
here.
considered in half.
Yes, yeah, so this is worth 8 points.
I didn't know.
Can you explain? I just want to know.
Which one? Number 1. So, you have the right idea, but if I want a vertical tangent line, it's gotta take on the form of x equals. So I gotta put this back into the equation to find what x equals to actually create. Because right now you're doing the, it's not a vertical. So it has to, and when you solve for y, you're gonna get plus or minus 1. So. Plus or minus 3.
No,
no, never mind. I must have missed that. Square.
Oh, okay, okay. Yeah, don't forget, your AP Franklin 5.3, I'm gonna check 5 through 10 tomorrow. So 5 through 10. You guys did 1 through 4 last night, you'll do 5 through 10 tonight.
Inverse me more then you gotta find. Once there's like your results of your original. Consider that so like nothing like.
It's not pretty good, right?
Let me look.
It's I mean, it's not about really, but why can you get like that? Because that's the and it says that here. It's you need, it's you need a. If I do. One thing I got this.
Yes, I got both. Yeah, so the 2 negatives will cancel out.
Okay, okay.
That's it.
This one. Yeah. I mean, that's my waiting point.
Yeah.
Yeah.
No.
Sorry.
I don't remember last year.